This lecture introduces matrix equations AX equals B, where A is a matrix, X is a column vector, and B is another column vector. So if we consider a system of M equations and N variables, so we have M number of equations and we have X1, X2 to Xn, right? And the B's here are constants on the other side of all the equations. Well, we can use a matrix to represent all coefficients of all the variables in all the equations, okay? Which is called the coefficient matrix. So this is the coefficient matrix from this linear system. Okay, and then we have a column vector X. Here, this column vector X contains all the variables of the system, X1, X2 to Xn. And then on the other side of the equation, we have a column vector B, right? That contains all the constants on the other side of the system of the equations. So then now let's look at the size or the dimensions of each of these vectors or each of this matrix here. So first, the coefficient matrix is M, right? It's an M by N matrix. And this variable matrix or variable vector or the column vectors that contains other variables has a size of N by 1, right? It has N rows and only one column. So if you multiply these two matrices together, well, this is the column vector is also an N by 1 matrix. Then you should expect a matrix of size M by 1. And that's exactly right? The constant column vectors here is a vector, column vectors, or a N by 1 matrix that contains all the constants on the other side of all this equation. And there are M number of equations. That means you have M real values in this vector or in this matrix. That's why the dimensions of this matrix here is N by 1. And that works out, right? So a matrix N by N multiplied to a matrix N by 1, you will get out a matrix N by 1. So this equations here is a matrix equations that is the representations for this linear system of M equation and N variables. And if you want to double check whether this is the right representations, you can try to multiply, so try to take the first row of this coefficient matrix and then you dot product to this column, right? To this matrix, to this column vector. If you dot products, the first row to this column vector, so this variable vector, you will get A11 times X1, right? Plus A12 times X2, plus A13 times X3, and so on and so forth, and plus A1n times Xn equals to B1. All right, and then that will be the first equations of the linear system. A11 x1 plus A12 x2 plus A1n x1 equals to B. All right, this is how I checked whether this matrix equations is a good representation for this linear system of equations. Okay, let's do a couple of examples here. So rewrite the following system in the form of matrix equation. So this is a system of 1 equations and 3 variables. 1 equations, right? And 3 variables. Okay. That means from this system here, I can find the coefficient matrix, which is only 1, 2, and -1. Okay. And then you have 3 variables, so that means your variable vector has to be has 3 entries. And then your constant vector or the constant matrix should be just 5. Again, this is the coefficient matrix. And then this is your variable matrix or column vector, right? It is a vector. And this is your constants matrix or constant vector. All right, now go to the second example. So second example, you have 2 equations and 3 variables. That means your coefficient matrix should have 2 rows and 3 variables. So you have the first row will be 1, 3, 0. The second row will be 2, -1, and 1. For the first row, there's no x3. That means the coefficients for x3 should be 0. Okay, this is the coefficient matrix. And you still have, 3 variables. That means the variable matrix should be x1, x2, and x3. And you have 2 equations. That means your constant matrix should have 2 entries. Okay. The size of this, we're going to check the size. So the size is 1/3, and this is 3/1. And the results is going to be 1/1. Second equation is 2/3, 3/1. You will have 2/1, which makes sense. All right. So once we learn how to transform a linear system of equations into matrix equation, then you're wondering the constants matrix, the B's matrix here, how this B matrix related to the coefficient matrix in terms of the number of solutions that you would have for a given system of equations, right? Is there any relation between this B matrix here with this coefficient matrix? So then we would know when we will have a consistent system or an inconsistent system. But the next concepts that we want to discuss is called linear combinations. So linear combinations, by the definitions, if you have n vectors in Rm and you have C constants or C or n number of scalars, C1, C2 to Cn, then the sum of the form C1A1 plus C2A2 plus CNAN is said to be a linear combinations of these vectors A1, A2 to AN with weights of C1, C2 to Cn. Again, A1 to AN are vectors, column vectors in Rm, right? And then C1, C2 to Cn are scalars or just constants. Then if you take C1, which is constant, multiplied to a column vector, plus C2, A2, plus Cn, An. And this result here is called a linear combinations of these n vectors A1 to An with the weights of C1 to Cn. Again, this result is just a column vectors in Rn. And just keep in mind, because A1 to An are in Rm, and if you multiply to a constant, those vectors are still in Rm. And if you add all the vectors in Rm, the linear combinations here is still in Rm. All right. And from this linear combinations concept or idea of linear combinations, we can try to connect linear combination with matrix equations, which is a system of linear equations, right? So if we consider a matrix A of size n by n and a vector x, a column vector x in Rn, then if you take A multiplied to x, this is, you take a matrix A and then you multiply to x, you will get x1 A1 plus x2 A2 plus xn AN, okay, where A1 to AN are the column vectors of A. All right. Then we can talk about the next theorem is the consistency theorem of linear systems. So we know that AX here is a linear system of equations, right? And then x1, A1, x2, A2, xn, AN is the result of A times x. So then if x1, A1 plus xn, x2, A2 plus xn, AN is equals to B. Well, B is B here should be a column vectors as well. Okay, then you will have the system of equation AX equals to B. All right. If B, the vector B here, equals to x1, A1, x2, A2 plus xn, ANs, that means B is a linear combinations of column vectors A1, A2 to AN. Okay, keep in mind, with the weight of x1, x2 to xn. Okay. All right. So the consistent theorem of linear system says, if you consider a linear system AX equals to B, and you know that this system is consistent, that means the system has at least one solution, if and only if the constant vector B can be written as the linear combinations of the column vectors of A. All right, so the system AX equals to B is consistent if and only if B is the linear combinations of column vectors of A. If we look at these equations here, right? If AX equals to B, and if B is written in the form of linear combinations of A1, A2 to AN, where A1, A2 to AN are the column vectors of A, then the system AX equals to B is consistent because you know there exists a vector X, X1, X2 to Xn, that satisfy the system. Because B is a linear combination of A1 and 2 to An with weight X1, X2 to Xn. That means the vector X here is a solution of the system AX equals to B. Okay. So let's try an example. If you have a matrix A, this is matrix 2 by 2, right? And B is a column vector 2 by 1. C is another column vectors 2 by 1. First thing you want to do is you want to write B as a linear combinations of the column vectors A1, A2. So if A is this matrix, then the column vector A1 equals to 1, 1, okay, and A2 equals to 2, negative 2. All right. So if we want to write B as the linear linear combinations of A1 and A2, that means if B is a linear combinations of A1 and A2, then there exist constants, right? Let's say C1 and C2 such that C1 times A1 equals to C2 times A2. C2, A2 plus equals to vector B. All right. So now if this is A1, this is A2, and you want to add A1 and A2 equals to B. This is A1, this is A2, right? And I want to plus 2, negative 2 equals to B, which is 4, 0. All right. Well, this is C1 and C2 should be here, right? C1, A1 plus C2, A2 equals to B. What values of C1 and 2 will satisfy this equations? Well, I would think if C1 equals to 2, well, 2 times 1 is 2 plus, and if C2 equals to 1, then, so if C1 is 2 and C2 is 1, we see that 2 times 1 plus 1 times 2 is 4, 2 times 1 plus 1 times minus 2 is going to be 0. So since I could find C1 and C2 easily by guessing, I know that C1 is 2 and C2 is 1. C1 equals to 2 and C2 equals to 1. Okay. Then if I replace this, by 2 and 1. This would be the right equations, right? So that means B equals to 2A1 plus 1A2 is your solutions. So B equals to 2A1 plus 1A2 is the answer for part A, right? Write B as a linear combinations of column vectors of A1 and A2. All right, how about 2? Use the result from part A to part A, which is part 1 here, to determine a solutions of the linear system AX equals to B. Does the system have any other solutions? Explain. So when you have a system AX equals to B, that means the system AX equals to B is equivalent to the system 1, 1, 2, negative 2, right? Multiply because it's two variables, x1, x2 equals to 4, 0. This is the system that we're talking about, AX equals to B. And we already found that B is the, and we found B equals to 2A1 plus 1A2. First, x1 equals to 2 and x2 equals to 1 is a solutions for AX equals to B. Right, if you plug x1 equals to 2 and x2 equals to 1, you will get the solutions. This is 2, this is 1. You will get 4 and 0, which is B, right? In order to answer the question, does the system have any other solutions, we can try to find the reduced echelon form, the row reduced echelon form of the matrix A to answer that questions. So if A, again, equals to 1, 1, 2, negative 2, if you reduce this, right, then that means you want to make this equals to 0. So I would, the 2, 1, I would take R2 equals to R2 minus R1, for example. Then my new row 2 will be 1 minus 1 is 0, right? Negative 2 minus 2 will be negative 4. Okay. And if you look at this reduce, the row echelon form, this is the row echelon form, almost the row echelon form of A. Then you can see that, okay, now we have one pivot. This is the pivot positions, which is the pivot column. So the first column is the pivot column. And this is also another pivot position. So the second column is another pivot column. Okay, so you only have two columns, and that means you have two variables, and both of them are pivot columns. That means you have, so that means you will translate this system into two leading variables. So you have two leading variables. So this is x1 is one leading variable, x2 is another leading variable, and you don't have any free variable. So this is pivot column. Okay, so both columns are pivot columns. That means you have two leading variable. That means you have no free variable. And since your system is consistent because it has at least one solution, and it has no free variable, and the system is already consistent, right? So this conditions here would tell you that the system AX equals to B has a unique solutions. Again, it has one solution, so it's consistent, and it has no free variable. That means it has a unique solutions. Remember, if you have at least one free variable, and if your system is consistent, then your system has infinitely many solutions. In this case, you have a unique solution. That means this is the only solutions. All right. Next part, you have a different column vector C, -3, -2, and you want to write C as a linear combinations of A1 and A2. So C equals to, well, this time I'm not calling it C1, C2, or equals to, let's say D1, A1 plus D2, A2. Okay, again, A1 and A2 are column vectors, and D1 and D2 are just constants. So you want to rewrite the column vector C in terms of like A1 and A2 as a linear combination of A1 and 2. That means you need to find D1 and D2 that satisfy these equations. Okay. In this case, to be honest, it's a little hard to guess compared to the vector B up here. Okay. C would be -3, -2. So what is D1 and D2? If I think it's a little hard to guess, then I would transform these equations into matrix equations, right? So I would have matrix A, 1, 1, 2, -2, and D1 and D2 would be a column vector, right? And equals to -3, -2. And in order to find D1 and D2, remember, you just need to transform this into an augmented matrix, because this is a linear system of equations. You want to transform it into an augmented matrix here. And you solve for this system. That is when you finding D1 and D2, which are just the variables. How can we solve the system? We know that we need to transform this into either a triangular form or the reduced row echelon form. So let's put it in just the triangular form. And we already did some reductions up here, right? So we just take row 2 minus row 1 and replace this to row 2. So I would just copy what I did up here. 1, 2, 0, -4. But now I need to incorporate this vector C here. And it were R2 minus R1. So -2 minus -3. So -2 plus 3, which is 1. Okay. So at this point, I know that -4, so it's just like x1 plus 2x2 equals -3, and -4x2 equals to 1. So if I translate this augmented matrix to a system, okay, and at this point, what do we know about x2? So x2, right, from this equations, x2 equals to -1/4 Well, how about x1? x1 equals to -3 minus 2x2. So -3 minus 2, -1/4 equals -3 plus 1/2. You get -5/2. Okay, so x1 equals to -5/2. So I'm used with x, but in this case, we need to have d, right? Because we're using d, not x. So I'll replace this by d1, d2, and up here, d1, d2, and d2. Again, d1 is -5/2, and d2 is -1/4. So now we can replace d1 and d2 here by its actual value, right? d1 -5/2. d2 is -1/4. Well, then this will be C now is a linear combinations of A1 and A2. Next, we're going to try a different types of questions. This is not a computational question. It's more or less like a proof problem, right? You know some information about a matrix A, which is a 3×4 matrix. You know information about vector B, which is a linear combinations of A1, A2, A3, A4, where these vectors here are the column vectors of A. Then what can you conclude about the number of solutions to the linear system AX equals to B? Explain, right? Let's write out what we know. So what we know is, first, A is a 3×4 matrix. So 3 rows and 4 columns. And you have column A1 here, A2, A3, and A4, right? You have 4 different columns. And you have 3 different rows. All right. And then we know one thing is B, so this is A. And you know a vector B is a linear combinations of A1, A2, A3, A4. Okay, that means B is a linear combinations of the 4 vectors, column vectors. A1, A2, A3, and A4, right? With weight, with scalars 1, 1, 1, and 1, right? Because 1 here, 1 times A1 times A2, 1 times A3, 1 times A4. Okay, so this is information that we know about, first the vector B, and second the matrix A. Okay, if you're thinking about the system AX equals to B, then you can think of the matrix A and then you augment matrix A, and then you multiply, right, to this vectors X. And since we have 4 columns, A has 4 columns, that means you have 4 variables. So this is X1, X2, X3, X4. Okay, and then you set it equals to the vector B. Vector B will be, you will have 3, because you have 3 rows, which is 3 equations. So vector B will be matrix 3 by 1. Okay, well, from this informations about B is a linear combinations of A1, A2, and A3, and A4. We know that the system here, since B is a linear combinations of column vectors of A, since B is a linear combinations of column vectors of A with weight scalar 1, 1, 1, then from here we know that 1, 1, 1, 1 is a solutions to the system AX equals to B. Okay. Because if you plug 1, 1, 1 here, A1, the column vector is A1 times X1, X2, X3 plus A2, so on and so forth. You will get the column vectors B. Okay, so if B is a linear combinations of column vectors of A with weights or scalar 1, 1, 1, then 1, 1, 1 here is a solution to AX equals to B. That means the system AX equals to B is consistent. Well, it has at least one solutions, right? Okay, but A is consistent doesn't mean it only has one solutions. Sometimes some systems can have infinite many solutions. How do we know whether this system here has only one solution or infinite many solutions? So now we're going to analyze matrix A, right? So from here we know that AX equals to B is consistent. That's one thing. It has at least one solutions. But does it have many solutions? We'll see. So now we're analyzing A. So A is a 3 by 3 matrix, a 3 by 4 matrix, okay? So if I translate this system into an augmented matrix, I still have A1, A2, A3, A4, right? And then I augment it with B. This is vector B. Okay. So I want to say A1, A2, A3, A4, and I have 3 columns. 1 column, 3 rows, 1 row, 2 row, and 3 rows. Okay. And again, this vertical bars here just separating the coefficients matrix with the constants. All right. So this is B, this is A1, A2, A3, A4, 3 rows. All right. So if I want to solve for this system, I want to reduce it. If I reduce this matrix, this now is matrix 3 by 5. If I reduce this matrix to the reduced row echelon form, since I have 3 rows, 1, 2, 3, then I would have at most 3 pivot columns, because each pivot position locates in 1 row. So since I have 3 rows, then I have at most 3 pivot columns. So let's say 1, 2, 3, 4, right? And then I have a vertical bar here, and then I would have my B here. Okay. So in this one, I would have, and then I still have 3 rows. 1, 2, 3. And then you can see here, let's say this is 1 pivot positions, right? And this is another pivot positions. And since I only have 3 rows, I have at most 3 pivot positions. If I have at most 3 pivot position, that means I have at most 3 pivot columns. If I have at most 3 pivot columns, that means I would have at least 1 free. Again, if I have at most 3 pivot columns, then I have at least 1 free variable. If I have at least 1 free variable, that means my system here is consistent and has many solutions. Infinitely many solutions.